What's up, guys? This is Matthew Burns, and I don't even know what tutorial this is, but this is in the video series on how to build an 8-bit computer out of individual logic gates. It's probably been a year, almost a year, since I posted my last tutorial. I've been busy, so I have to apologize for that. But in this tutorial, we will be, I guess, what do you call it? Circuit deriving. Sure, we'll go with that. A schematic for the positive edge trigger D flip-flop, which is what we are going to be using to store 1 bit of data. We are going to be using these positive edge trigger D flip-flops to store 1 bit of data. We're going to use 8 of them in, I guess you could say, in parallel to store a byte of data, and that will be 1 byte of data, so 8 positive edge trigger D flip-flops will make up 1 register for our computer. So I'm going to start by going over what we are trying to come up with, what we are trying to I guess you could say, derive a schematic for. So we want some device. We don't know what it is yet, but we want some device, denoted by that blue box that you can hardly see. And we want it to have 2 inputs and 1 output. We want it to have a data input. We want it to have an enable input. We want it to have an output denoted here with Q. And what we want this device to be able to do is store whatever data is on the data line into Q whenever enable is brought from low to high. So whenever enable, if you look at this here as a voltage versus time, maybe something you'd see on an oscilloscope or something like that, just part of a square wave, as enable, logic level 0, logic level 1. We don't want D, whatever is on D, to be stored on Q when enable is high. We don't want whatever is on D to be stored on Q whenever enable is low. Only on this transition, when enable switches from low to high, we want whatever is on data to be stored on Q. So we're going to accomplish that using Nand Gates. So first we are going to discuss what the Nand Gate is. You can think of it as an AND gate that has its output inverted. Its symbol is very similar to that of an AND gate, but it has that small little circle at the top. And similar to the AND gate, it has 2 inputs and 1 output. And before, well, actually, forget what I just said, because you'll see even later in this tutorial that it can have more than 2 inputs. It could have 3 inputs. It could have 4. That's really dependent. So it could have more than 2 inputs, but it will have 1 output. And so I am going to go over the first. I should tell you also another convention that's pretty much universal, but that we're going to be using in this tutorial. I'm going to denote positive logic levels with red and ground or low logic levels with 0. So that is the schematic or drawing for a NAND gate. I'm going to go over the logic table for that. So I'm going to label this input A, this input B, and I'll just label this output C. So if we draw a table here, those are our 2 inputs. Here's our output. There are 4 different possibilities for inputs on this NAND gate. We could have a 0, 0, 0, 1, 1, 0, or 1, 1. The way this NAND gate works is as long as A input is low, or I shouldn't say A input because I'm not referring to input A, as long as there is a low input, the output will be high. If both inputs are high, the output will be low. So with a NAND gate, the output is high unless both inputs are high. So that's pretty easy to remember. It's just like an AND gate, except the output is inverted of what an AND gate would be. So the basic unit of memory storage that is going to be used in this positive edge trigger D flip-flop is something called a set reset NAND latch. And that is created, it is very similar if you know what the SR NOR latch is, which we're not going to be going over. It's not in the scope of this tutorial, but it's basically the same thing. If you understand one, you understand the other. Set reset NAND latch is created with 2 NAND gates, and the output of one is fed back to the input of the other. And so you're left with a device that has 2 inputs, and technically it has 2 outputs. This here is our output Q, and this I guess you'd call Q bar. It's Q with a little dash over it. We're going to completely forget about it. We're just going to deal with output Q and our 2 inputs. So that is the set reset NAND latch. Set reset NAND latch. We're going to be going over, before we go into the positive edge trigger D flip-flop, I would like to go over the data table for this set reset NAND latch. So again, I'm going to label this A, this input. This input's going to be labeled B, and our output here I'm going to label Q, as that's how it's done by convention. So if I draw the data table here, we have A, we have B, we have Q. Again, there are, just like with the data table for the for just the NAND gate, there are 2 inputs, so we have the same possibilities for combinations for an input. We have 0, 0, we have 0, 1, we have 1, 0, and we have 1, 1. Those are the 4 different possibilities for inputs. Alright, so I'm going to start from the top and move down. And there's one thing that's kind of irregular about this first set of inputs here, 0, 0. That is what is called a restricted or forbidden combination with the set reset NAND latch, because something fairly peculiar happens if you set both inputs A and B low, which I'm going to draw here for you. So now we just set both inputs A and B low. If you recall from the data table or logic table for the NAND gate, if any input is low, the output is high. So if both inputs are low, A and B, both of the outputs of the NAND gates are going to be high. And all's fine right now. That looks fairly stable. Each one has a low input, each one has a high input, so the outputs for both are held high. And it looks fine right now. The trouble happens when you turn both of these inputs high again. So let's say both inputs are low, and now we're going to turn both of them high. I can talk through the rest of this, but I can't keep drawing this because a lot of stuff's going to start changing really fast. So both inputs were low, and now we set both inputs high. Now if you remember from the data table for the SR NAND, or for just the NAND gate, if both inputs are high, the output's low. So in a perfectly ideal world, both of these were switched high at the same time. Both NAND gates see 2 high inputs, and so both NAND gates will have a low output. Well, if both NAND gates read their inputs that are fed back to one another as low, they'll both have a high output again. And then they'll both read their inputs fed back to one another as high, and so they'll both put out a low signal. And in theory, that should just keep oscillating back and forth, but in reality, you know, maybe resistance in the circuit, length of traces, a lot of different things could affect this. And so it'll usually stabilize in an actual situation. It'll probably stabilize as one being the same almost every time, or more often than not. And so it will eventually stabilize as Q being high or Q being low in the other one, Q bar, I guess, being high or low, whatever Q isn't. But you don't know what it's going to stabilize at. So that is the forbidden situation, forbidden combination, because it's not a stable state. When you bring both inputs low and then you let them go both high again, the NAND gates will be unpredictable. They'll keep oscillating back and forth until they settle at one being high and one being low. So that is something that we don't, that is one state, one set of inputs that we don't want to set the NAND gates at. So 0, 0 is no good. I'm just going to cross that off. Another set of inputs we could have is 0, 1. Actually, I'm going to go over that one later because I want to be able to see change on this SR NAND latch when we do something. So we're going to work on input set 3, 1, 0. So we're going to see what happens when we drop B low. When we drop B low, you'll notice before it had too high input, so its output was low. Now, the NAND gate on the right has a low input, so its output is going to be high. So the output of B is now high. And if you notice, A now has 2 high inputs, so the output of A is low. It's all straightforward so far. Now if you notice, back to the NAND gate on the right, it has 2 low inputs, and the NAND gate on the right has 2 high inputs. There's no problems with this setup here. It's a stable state, unlike state 0, 0. And what happened was when we dropped B low, you'll notice Q also dropped low. So on this logic table here, we're going to fill out, we're going to put a 0 there. When we drop input B low, Q will drop low. I think next I'm going to cover state 1, 1. State 1, 1 doesn't cause any change in the circuit. It merely holds the set reset NAND latch at whatever it was at. If you'll notice, if I bring B high again, so it's at state 1, 1, nothing changes because the NAND gate on the right already has a low input, held low from this other NAND gate. And so, whatever changes we make here to the circuit by bringing B high does not propagate through the rest of the circuit, and it remains unchanged. So, a logic state for the SR NAND gate 1, 1 provides no change. I'm just going to denote that with a dash. Now, the SR NAND gate is in a state such that we'll see change if we bring about these logic levels to their respective inputs. So we are going to drop A low, and right now we're testing the second set of possible logic levels for the inputs. We're going to drop A low and leave B high and see what happens. When we drop A low, you'll notice before A had 2 high inputs. Now A does have a low input, so the output of the NAND gate on the left goes high. And the NAND gate on the right has 2 high inputs, so its output goes low. And just like we saw before with A being high and B being low, we again have a stable state, but this time A is low and B is high. And if you'll notice, in this stable state, Q is high as opposed to low. So what happened here is when we dropped input B low, Q went to a low logic level. When we dropped input A low, Q went to a high logic level. When we change both inputs to 1, 1, nothing changes because this input on this NAND gate is logic level low, and so this output on this NAND gate doesn't change, and so whatever changes we make here to this circuit by bringing A high does not propagate through the rest of the circuit, leaving everything else unchanged in Q high. So that is the set reset NAND gate. 0, 0 is a forbidden combination. Don't use it. You won't know what you're going to end up with for Q. 0, dropping A low brings Q high. Dropping B low brings Q low. And 1, 1 will just store the data at whatever it was at. So now we are going to complicate things a little bit. We are going to basically use, we're going to basically make almost a complete set reset no, my bad. We are going to almost completely make a positive edge triggered D flip-flop, though we're going to make a few adjustments to it until we get to the actual schematic for a D flip-flop. The D flip-flop is going to be created using 3 set reset NAND latches. So I'm going to redraw the data table for the set reset NAND latch in the upper right hand, upper left hand corner of this board here, and then we will begin with the rest. Okay, what's up guys, this is Matthew Burns, and I'm going to attempt to explain this a different way. I'm going to draw out set reset NAND latch, and I'm going to draw out 2 other set reset NAND latches to store the input of that main set reset NAND latch. And then we're going to go from there to what is the schematic diagram for the positive edge triggered D flip-flop. So before, we discussed and went over the data table for the Nand Gate and set reset NAND latch. So I'm going to end up drawing 3 set reset NAND latches here. We have the main set reset NAND latch at the top, and that is what will hold the output Q. And again, the set reset NAND latch that's fed back to the input of the other NAND gate. We have the output Q bar, which we're not even going to label because we're not going to make any use of Q bar whatsoever. And then we have the 2 inputs. Now the 2 inputs of these set reset NAND latches are going to be controlled by the output of these set reset NAND latches down here. And right now they just look like NAND gates, but one side at a time I'm going to draw the wires to make each of them set reset NAND latches. There we go, that one's complete. And exact same thing on this side. Now, if you remember at the very beginning of this tutorial, we went over what we wanted out of this device. We wanted something that has 2 inputs, data and enable, and we wanted something that has 1 output, Q. So we have the output. Now, with the rest of the inputs from these NAND gates, we have to produce a data and an enable input. The enable is simple. If you look, while these are set reset NAND latches to store the inputs, you also have to think of them as, you kind of have to look at them as individual components. This is one NAND gate here. If we discussed the data table for the NAND gate and determined that as long as 1 input is low, 1 or 2, but as long as there's at least 1 low input, the output will be high. And you remember, for the set reset NAND latch, if both inputs are high, then the data is saved. So what we can do is we can wire both of these NAND gates up to the same enable, and as long as enable is low, these 2 wires will always be high. The 2 inputs to the main set reset NAND latch will always be high, as long as enable is low. And Q will remain whatever it was previously at. Will remain as whatever it previously was. The tricky part in making the set reset NAND latch is the data. When we switch enable high, whichever one of these drops low depends on the input of this NAND gate on the right and this NAND gate on the left. And there are 2 inputs left and 1 data. So since we only want to drop one of these low at the time, at any given time, we're going to have data be given to one of these NAND gates and an inverted copy of whatever that data is to the other NAND gate. So I'm just going to draw the one at the right as receiving data, and the one at the left, that's a really bad inverter. Just pretend. The one on the left will be receiving an inverted copy of whatever data was. And so, if you'll notice, now we have a pseudo-functional set-reset NAND latch. So instead of going through a data table for this whole thing, because it's kind of complicated and confusing, I'm just going to be talking over changes we make, what happens when. So if you'll notice, when I turn data high, actually, nope, in order to see change in Q, I'm going to leave data at whatever it's at now. So if you notice now, this is true data, this is just an inverted copy of it. Data is low. When I turn enable high, what we want to see happen is we want to see Q go low. So I'm going to make enable go high. And see what changes that brings about. Alright, right now it's looking like it's bringing about no changes, but that's because there are errors in this. And it is on this side here. I drew data, but I forgot to change the outputs of the NAND gates accordingly. So if you notice, data is a low input on this NAND gate, so this NAND gate has a high output. Just like that. And so, when we flip enable high, nothing changes here because this is a low input, but this side has two high inputs, and so this NAND gate will drop low. Now, no further changes are going to occur in the circuit. Two low inputs on the NAND gate on the farthest right will sustain the high output on the NAND gate on the far right, and nothing further will happen on the NAND gates in the far back. On the NAND gates on the top, you will see change. This NAND gate now sees a low input, so it will produce a high output. This NAND gate will then see two high inputs and produce a low output. And that will be sustainable. I'll draw that out the first time. So this here will go high. This, which is Q now, will drop low. And so what we just saw happened is when we turned enable high, Q mirrored data, which is exactly what we wanted. Now, if you'll notice, when we turn enable low again, it doesn't matter what happens to data, when we turn enable low, nothing happens on the left side, SR NAND latch, because it already had a low input, so the output was high. The no changes propagate past that NAND gate. However, on this NAND gate, now it does see a low input. And so this whole wire here will go logic level high. And no changes propagate past that NAND gate because it sees data as low. And so, the inputs to this front set reset NAND latch, if you look at them as a whole, are 1, 1, and so Q is stored low. So this is a pseudo-functional set reset NAND latch. It'll work to store data, but there are a couple of problems with it. The first problem is that you can change you can change the data when enable is high. That is the first problem that we have to fix. Because we wanted a device, I'm going to draw a waveform to the left. We wanted a device, if this here is enable at logic level low and logic level 1, we wanted a device that only stored whatever was on data onto Q on that rising edge right there. Well, right now we have something that will not store data when E is low, but it will store data when enable is high. And so we have that whole upper edge of the waveform that we have to see if we can get rid of. So the first thing that we're going to do to change this step is we are going to, I know I mentioned this earlier, we are going to add a third input to each of these NAND gates. And I'll explain why as soon as I finish drawing these. Now, the logic for a 3-input NAND gate is identical to that of a 2-input NAND gate. The output is high unless all 3 inputs are high. If all 3 inputs are high, then the output is low. Otherwise, the output is high. And if you see what I just did, I just simply took the output of this NAND gate and I wired it to that NAND gate, and then I took the output of this NAND gate and I wired it to that NAND gate. Now that is not how the positive edge triggered D flip-flop is wired, and that has to do with the fact that we're using this NAND gate as an inverter for data, which we'll get into later. But first we're going to discuss this way. So what this did is it will prevent us from being able to cause any changes to these here, to these wires here, the inputs to the main set reset NAND latch when enable is high, or when enable is high. So when we turn enable high, one of these two wires will drop low. That depends what data is, but one of these two will drop low. And to prove that point, we already saw the, might have been the right side one. Yeah, the right side one drop low. So I'm going to change data so we can see the other one change, just so we can see that this set reset NAND latch is functioning properly. I'm going to make data high, and what you just saw me draw was the inverse of data. Data is on this side. We're going to make any changes to these NAND gates that's necessary before we change enable. I won't make the same mistake twice. The NAND gate on the far right has 2 high inputs. It will produce a low output. This 3-input NAND gate, which is looking kind of messy at this point, does have a low input and had a low input. The output was and still is high. It does not change. So that's the extent of what happens there. On this side, this had 2 high inputs, so it had a low output. Now it has a low input, so it'll have a high output. So I'll change this to high. And that is the extent of the change on this side, because enable is low, so nothing changes with that NAND gate. Now, what'll happen when I switch enable high? I am going to turn enable high. And if you'll notice, nothing happens on the right-hand side because the 3-input NAND gate on the right-hand side has a low input. On the left-hand side, all 3 inputs are high, so the output goes low. It's getting kind of messy. I'm hoping you can still follow along. I'm having trouble myself. So, the output to that 3-input NAND gate is low, and the only other changes that are going to occur to this schematic are at the main 3-input NAND gate at the top. The main SR NAND latch at the top. The NAND gate on the left sees a low input, so it'll have a high output. And the NAND gate on the right sees 2 high inputs, so it'll have a low output. And Q just switched high. So if you notice, the circuit still functioned just as it did before. When we turned data low, turned enable high, Q dropped low. We turned data high, turned enable high, Q was pulled high. The difference is now that if you remember, we said we don't want to receive a low, low as an input for a set reset NAND latch? Well, if we changed data, that is exactly what we would see, because we would turn this input low, this would go high. Alright, sorry about that. I lost my train of thought again. Things get confusing here. So, what we most recently added and tested was the 3 inputs on each NAND gate. The purpose of the 3 inputs on the NAND gate is to keep the input to the main set reset NAND latch on their respective sides high when they're supposed to be. If you toggle the data when the enable is high, you could see one, if you didn't have the 3 input NAND gate, you could see both inputs going low, and that's a situation that we don't want. So, if you'll notice, when this input is, we established before that when enable goes high, one of these 2 inputs will go low. These, I'm referring to them as inputs because they're inputs to the main set reset NAND latch. One of the 2 inputs will go low. That depends on what data is. If we toggle data when enable is high, we could see the other one going low as well, and then we'll reach the forbidden combination for the main set reset NAND latch, and we don't want that. So we need a way to keep the one that's high from going low. So what we do is we have a wire go from those inputs to the main set reset NAND latch to a 3 input NAND gate instead of 2 on the other set reset NAND latch in the back. What that'll do is, let's say this one drops low for whatever data is. This one drops low. If this input to this set reset NAND latch drops low, this 3 input NAND gate will have a low input, and so its output will always be high. It does not matter if we toggle data, make data go low, have this input be high, and this will not be able to drop low because this input here is high. Or, I said that completely backwards and wrong. When this is low, this cannot drop low because this 3 input NAND gate has a low input. And the same would be true in reverse. If this side were to be the side that dropped low, this wire here, this input to this NAND gate here, would not be able to drop low because this set reset, or this 3 input NAND gate would have a low input here. And so by having the output to these 3 input NAND gates go to the input of the other 3 input NAND gates, you effectively keep the 0-0 forbidden combination for the main set reset NAND latch from being achieved. There are 2 other changes we're going to make to this before we get to the positive edge trigger D flip-flop, and that is data. Now, we only want data to be... So basically, what we just did is we enabled this, so any changes we make to data when enable is high will not be propagated past this part of the circuit. Nothing up here will change if we change data when enable is high. And that's what we want. That means we finally achieved this here. Q will only follow whatever data is when enable is turned high. Just on the positive edge, not when enable is high the whole time. Just on this rising edge will Q follow data. And now that we have that achieved, we're just going to do a little bit of cleanup work on this circuit to make it... I guess we could remove an input on one of those 3 input NAND gates, and I'll explain that in a little bit. And we can remove an inverter. Now, we established before that whenever enable was low, both of these will be high. Well, we're going to take advantage of that to use this as an inverter, and I'll show how in a minute. We only want to be able to change data, and now it is only valid to change data when enable is low. So we only need something that works as a valid inverter when enable is low. So, if you'll notice, when enable is low, this by definition has to be high. And so the input to this NAND gate is high. Now if you'll notice, I'm going to draw the logic diagram for, this is for just an individual NAND gate. And that's it. Not a set reset NAND latch or a positive edge trigger D flip-flop, just a NAND gate. We have 0, 0, 0, 1, 1, 0, 1, 1. This 0, 0 combination will have a high output, high output, high output, low output. Now, we're going to label this as A, pretend this input here is A, and this input is going to be B. B is going to be our data, A is going to be our enable. If you'll notice, we're only going to look at the scenarios when, or it's not really our enable, it's this wire here, which is held high when enable is low. We're only going to look at the scenarios when this wire is high. When that wire, this input A here is high, if you'll notice, C is always the inverse of B. When A is high, this output is always the inverse of this input. So, when A is high, this NAND gate acts as an inverter for data. This will always be the inverse of data when A is high. And A is only always high when enable is low. So whenever enable is low, this NAND gate right here will effectively work as an inverter for data. So what we can do is we can erase that inverter in the bottom left, just have data go to one NAND gate here, and use the output of it to go to the other NAND gate as the inverted data. That is one of the changes we are going to make. The other one is that we only need one 3-input NAND gate. The reason for that is because we use this NAND gate as the inverter and not the other one. If we use the other one as the inverter, we'd be erasing the other 3-input NAND gate. If you'll notice, when Q is high and enable is high, we'll run into a problem when we... Nope. Hold on. Okay, I'm back, and I am less confused than I was before. So, now I can explain this. Because this NAND gate here is the one we're using as the inverter for data, we will only run into the problem where we could achieve low-low by toggling data on one particular combination, when Q is stored high versus low. So when Q is stored high and enable is brought high, we'll run into the problem. When Q is stored low, so let's make this situation, we're going to bring enable low before we do anything else. Nothing happens on the right side. 3 low inputs are the same as 2. However, this entire setup, this entire wire here, will go high. Nothing changes at that NAND gate. Nothing changes at that NAND gate. So, what we're left with is 2 high inputs to the main set reset NAND latch, and that is a stable state. There we go. So the set reset, the positive edge trigger D flip-flop, which is the whole thing, will store whatever it was previously at. Now I'm going to make data low. Nothing will happen because enable is held low. But we talked about whenever enable was low, this will act as an inverter. So now with a low input, this will have a high output. Now with 2 high inputs on the left, this will have a low output. Nothing changes further on the left-hand side. On the right-hand side, nothing changes yet. So we are going to turn enable high, And at this point, you may notice this set reset or positive edge trigger D flip-flop is fully functional, but we can get rid of one of these 3 input NAND gates and still have it work perfectly. And that is what we're going to do. So by pulsing enable high, this entire wire here is going to go low. This is getting really messy, but hopefully I won't have to erase this too many more times. It's probably getting tiring to watch too. So by pulsing this low, this now has a high output, and this Q drops low. So if you'll notice, Q, again, mirrored data when I pulsed enable high. That's exactly what we wanted. And at this point, I am ready to demonstrate what the issue we are going to have is. When I turn, now, before, when Q was high, which it's not now, it's low, when Q was high and enable was high, when I changed data, both of these wires would have gone low. And that's why we needed this 3 input NAND gate to prevent this one from dropping low. Because of the NAND gate on the right, when this side drops low, this NAND gate no longer acts as an inverter, because no matter what data is, this output here of this NAND gate will be high, and so the issue with whatever data is changing will not propagate through this gate to this output. So, by changing data, whether data here is high or low, this output will always be high and nothing else in the circuit will change. So, we don't need, and the whole purpose of this 3 input NAND gate was to be able to keep this from dropping low, which was a problem caused by changing data. If data will not cause problems using this NAND gate as an inverter to this side of the circuit dropping low, we can erase this wire, simplify the circuit by 1 input, and turn this again, once again, into a 2 input NAND gate. And that is our completed set reset NAND latch. Did I say not a set reset NAND latch? That was what we discussed earlier. This is a completed positive edge triggered D flip-flop. Only on the transition from low to high for enable will Q mirror whatever data is. You can change data when enable is high, and Q will not change. You can change data whenever enable is high, and both of these will not drop low. Only one will drop low and will avoid the forbidden combination. You can change data when enable is low, and Q will not change. Q will remain Q unless data is different when enable pulse is high. So that is the circuit, the logic circuit we are going to be using for our registers. And I have an example over here. I'll go grab the circuit that I soldered together and show you what mine looks like. So this here is what my register looks like. It is nothing more than 8 of these side by side, because I want to be able to store 1 byte of data in a register, and each of these only stores 1 bit. This here has 8 input wires on the left, 8 output wires on the right, power and ground, the red and black wire by my thumb, and the green wire that you can barely see right here, which is the enable. And so I will draw up a complete schematic of the register. I'll show you it in use in the next tutorial. And this is pretty much it. This is a positive edge trigger D flip-flop, which stores 1 bit for our registers. So thanks for watching, and I'll see you guys next time.